All right, good evening, everybody. We are now live for the Triangle SQL Server Users Group. This is our January main meeting. We have with us Erik Darling. Before I hand it over to Erik to do his thing tonight, I have a couple of announcements. The first announcement is that we are on the way to SQL Saturday Raleigh 2020. So I've got a venue. Yeah, it's been quite a bit of time in the making. Got a venue pretty much locked down for April 18th, Wake Tech RTP. It will be a smaller event than in previous years because we could only get about half the rooms normally we would get. So there will be more news about that. I'll send out an email to everybody in the next week or so as we get paperwork signed. Also, Pass Summit registration opened up today, so it starts at $1,399 for the early bird edition. Pre-cons are at $499 a pop currently. I would expect both of those prices to go up over time because it's normally what happens. So with that, let me make sure that people in chat are able to hear me.
Hi, people in chat. Chat people.
And as soon as I get some level of confirmation from folks, then we will officially hand over. We have confirmation, so yes, I am not completely bad at this game.
That is awesome. I think this might be my first time on Twitch, so I'm just like so thrilled. I don't know what to do with myself.
I think it's time to play Overwatch.
It could be, yeah. I mean, I haven't played a video game since Team Fortress 2, so I don't know how good I'd be at anything. Terrible at everything. All right, is it my turn?
It is all you now.
Wow. Okay. All right. Well, welcome everyone. Thank you for showing up. I have no idea what the weather is like there. I know that here it's freezing. So if you braved any sort of freezing cold to attend this, I appreciate it. I hope the pizza was worth it. For everyone who stayed home, you're probably smarter than the people who braved the cold for that pizza. I don't know. Maybe you have great pizza. I've had pizza outside of New York. I didn't think much of it though. Anyway, I'm Erik Darling. If you ever want to get in touch with me about anything, well, not anything related to SQL Server, I pretty much just focus on performance stuff. I leave all the other stuff to people who can deal with infrastructure and tolerate availability groups and all that other Kubernetes, whatever noodles. But if you ever want to get in touch with me about performance things, which I love, which I am very much into, these are the three best ways to get in touch with me. I have a website. Shocking, I know. And that website also has an email address for it. And keep in mind that my name is spelled with a K like the Viking. It is not spelled incorrectly with a C, like probably someone sitting there who's now very mad at me. And if you want to talk to me on Twitter or follow me on Twitter or, I don't know, block me on Twitter, probably more probable outcome after this. My Twitter handle is at erikdarlingdata.com. I believe it or not, I did not pay anyone for this level of branding. I did it all myself. I don't know how you can. I don't know. You can, if you ever want to talk to me about branding, don't. If it wasn't my name, I would never have come up with it. So what I want to present to you tonight is a presentation that I put together because I didn't want to present about anything in particular. This is my SQL Server performance tasting menu, and this is just a bunch of stuff that I currently find interesting. It could be anything from one presentation to another. Demos might change, stuff might go crazy. Who knows? Maybe something broke since I installed the last cumulative update. I don't know. It's just kind of something that I have fun with. There are great people who are there are people in the community who are great storytellers who are great from taking you to point A to point B. I really just like kind of freestyling and going off and just showing you stuff that I think is kind of cool at the moment, because there's always something new and cool popping up when you're doing performance tuning. I mean, there's a lot of the stuff is, kind of like, Groundhog Day with like, yes, you have a function. Yes, you need an index. It's probably better if you put more than one CPU in the server, but there's all sorts of interesting stuff once you get past that. And that's the kind of stuff that I love. So let's get warmed up. And let's talk a little bit about trivial plans, because trivial plans are a really interesting thing where SQL Server just kind of says, whatever. Like the optimizer looks at your query and just says, I don't have time for this. Like I'm not going to, if I thought about a better way to run this query, for the next 30 years, I would not come up with a better way to run this query ever in my life. So how you can tell if you get a trivial plan is if you run a query and you hit the right button, if you hit execute rather, if you hit F5 rather than F4 and get off to a good start, you'll see a query plan pop up. And this is something that you should always be doing when you're looking at query plans. Always hit F4 after you have the query plan. So like when the query plan pops up, this properties window that you can hopefully see over to the right is what shows up when you hit F4.
It is a little small for us.
It's a little small. I'm sorry. I can maybe do this and have it be bigger. Is that any better? Or is that change nothing?
Nah, it's the text size.
The text size. Well, if I can zoom in a little. I can zoom it. There we go. So the properties window will show you all sorts of interesting things. Not where it currently is, but when we change it, when we flip around and we actually get on an operator, we can see all sorts of interesting stuff about a single operator. Like this one, we can see that the optimization level was trivial, and that will have some effects on our query and our query plan, which we will get into. Now, what I want to point out is that you can do some kind of funny things and still get a trivial plan. Like things that you think what might be complicated or might force the optimizer to have a choice to make. You can do some stuff and you can not end up with a fully optimized plan. Like if I go over here and I click and I look at this, like that plan with the row number stuff was still trivial, even though, like this is probably a non-trivial amount of work just to remember the syntax for a row number query. Like that every time I have to look it up. What gets a query to the stage of full optimization beyond just getting a trivial plan is when you force the optimizer to make a decision. Like when you say, like, okay, optimizer, here's a query, and the optimizer goes, ooh, good one. So one way not to get a fully optimized plan is to select a distinct number of rows from a column that's already unique. And in the users table, the ID column is already the primary key. It's already the clustered index. So when we run this, there's no choice to make. The column's already unique. We don't have to go and make it doubly unique. We don't have to think about how to do that. But if we ask for a distinct set of rows from a column that's not unique, and the first inkling you might get that we got slightly different query plans is that the reputation column showed up in slightly different orders from one set of results to the other. And when we look over at the query plans, we can see that the optimizer made a choice between these two plans. We can see that for the top plan, for 1,000 rows, it choose to do a hash match flow distinct. I always get caught up on hash match. And then for the bottom query, where we asked for a top 5,000 rows, we did a full hash match aggregate. So the optimizer made a choice here. The choices that the optimizer makes are all based on costs. So the optimizer will take a look at a query, take a look at what you want it to do, start running the numbers on stuff, and it will pick the cheapest plan that it can come up with in a reasonable amount of time. That cost-based decision is what gets us to full optimization. So if we go look over here now and we zoom in over here, so you nice people who showed up either from home or in some kind of classroom setting, you can see the optimization level for these two queries is now full. Now, I said that you can do some kind of complicated stuff and still end up with a trivial plan. There are some things that are pretty obvious that will get a fully optimized plan. If you tell SQL Server to join two tables together, it'll spend a good amount of time thinking about how it wants to get those two tables joined. If you say you want to select some columns and you want that data to be ordered by a column that does not have a supporting index for that sort order on it, you will get a fully optimized plan. A good rule of thumb is that if you have a parallel plan, if your plan goes parallel, you do not have a trivial plan. There are some very goofy things that will get you a fully optimized plan. The only difference between these two queries is how I have the ID column selected. In this query, it is just select top 100 ID. And in this bottom query, it is the select top 100 select ID as ID. There's nothing logically different about this. There's no crazy where clause. There's no join. There's nothing in here for the optimizer to really think about. But if I run these two queries and I look at the execution plans, they will look nearly identical, except for this compute scalar. And this compute scalar is what SQL Server had to think really hard about. This is that, oh, how are we going to select ID? I don't know. How are we going to do it? And it's like freaking out about it. But this top query, again, if we got to toggle around a little bit over here, absolutely positively trivial. And this bottom query is absolutely positively fully optimized. Isn't that weird? That SQL Server fully optimized a query just to select ID from a table that it's already selected. Like, why? Like, I don't get that rule, but what the hell? Another kind of funny thing to do is this. We have one query that's select count from users. We have another query that's select count from users where 1 equals select 1. I'll zoom in on that. Hopefully, anyone sitting there who doesn't believe me, that is the end of the query. I have properly terminated both statements with a semicolon, and 1 is always going to equal select 1. There's no way around that. But the optimizer, again, goes into kind of a tizzy. We get the same count back, but this one up here, trivial plan, oh, that stinks. This one down here, fully optimized plan, boy, that's weird. Now, you're probably wondering at this point why I'm talking about trivial plans, why they might matter, why you think that, like, why are we spending the first 10 minutes of our night when I'm trying to go into my pizza coma talking about trivial plans? And it's because when a plan is trivial, you can miss out on some interesting optimizations. You can miss out on some feedback from the optimizer, and the optimizer can do stuff where it's actually counterproductive to have a trivial plan in place. So let's look at a couple examples. If I run these two queries and look at the results, this top query, where I've selected star from users where reputation equals 1, the optimizer says, oh yeah, no big deal. I'll just do that. The bottom query, where I have that other sneaky little extra bit of where clause, you can see that there's something a little bit different in there. They both cost the same, but that bottom query has a missing index request. If your query does not reach full optimization, you will miss out on missing index requests. Now, I'm not saying that you should always listen to missing index requests or that they're the most perfect, well thought out things in the world. After all, the optimizer is just coming up with them very quickly as it optimizes the rest of your query. Like, oh yeah, that might be good. But it's kind of interesting to know that stage of optimization is when those missing index requests get come up with. Now, I wouldn't add this missing index because it's bonkers. It's literally the entire table. If we look at it, like, this is a daft index. Like, this is basically adding a clustered, non-clustered index because it's a key column and then it includes every other column in the table. So if you add that, you're probably not very smart. But the optimizer is not very smart for telling you to add it either. So it's kind of, I don't know, like it's the blind leading the blind on that. But nice to know that the optimizer is sort of thinking of. Except when we see stuff like this, because if we wanted to be very diligent stewards of our data, right? We are diligent DBAs and developers, and we want SQL Server to perform as well as we can. So we're going to tell SQL Server exactly what values live in our reputation columns. They will always be greater than or equal to 1, and they will never be over 2 million. Because if they're ever over 2 million, someone has spent way too much time on the internet. Now, that constraint is trusted. And we know that because when we query the check constraints DMV, we can see that it is not trusted, right? So little double negative there, a little confusing, not well thought out on whoever created that DMV. Maybe it was Connor Cunningham. I don't know. He seems nice though. But when we run this query, right? Select display name, age, reputation from users where reputation is 0. That completely conflicts with our constraint up here. It should say you're greater than 1. But when we run this, our execution plan shows that we scanned the clustered index. There it is. We scan, wrong button. There we go. We scanned the entire thing. Here I am making fun of the optimizer that doctors work on, and I can't draw a pink rectangle right. That's just my kind of day. So we do scan the entire users table. And if we look at the stats IO from it, we can see that we scanned it once and we did 44,440 logical reads. I can't tell you how many times I've just wanted to insert enough data to put 4 more pages in there just to make this a nice even 4s across the board. But I'm also very lazy, and it would take me far too long to figure out how to get exactly 4 pages in. That would just be too challenging. I have too much other stuff going on. But if we run this query where we have the 1 equals select 1, this will get a slightly different execution plan. And rather than scanning the clustered index, we will have this constant scan operate, which means that SQL Server got to a further point in the optimization process, got to full optimization, and it said, that can't possibly be there. We're not doing this. I'm not running this query. And if we look over at stats IO on the messages tab, there is nothing about anything. There's no messages about IO anywhere. There's no messages about CPU having more than 0 milliseconds. SQL Server completely bailed on that on trying to run that query. It said, nope, not going to do it. That's ridiculous. There are no zeros in there anyway. Why would I waste my time? So trivial plans are kind of interesting. Oh, great. I have to restart. Can we pause while I restart for Windows Update? No? All right. So trivial plans pair sort of well if you are running very simple queries on a very small database and you don't ever care about having a fully optimized plan or getting any feedback from your query or having your query pay attention to little stuff like constraints or like barring keys or anything like that. If you don't care about any of that stuff, then I don't know, you probably wouldn't be here tonight. But if you do care about that stuff, then you got to watch out for trivial plans. Where I see them get people a lot is like on little entity framework queries where like, you're just constantly checking like some big users table to make sure that a user is in there, and you end up scanning the whole clustered index over and over again, and no one ever knows that you're doing all this extra work because there's never any feedback, and no one ever just kind of looks at that plan and says, oh yeah, we should maybe have an index that matches that where clause. That might be a smart thing to do, but people who write entity framework queries just ignore SQL Server anyways. What are you going to do about that? Were there any questions on that, or are we good to keep going?
We are good so far inside the room, checking to see if there are any questions in chat, but none yet.
Okay, well that's good. All right, so I'm creating some indexes here, and while I'm creating those indexes, which will hopefully not take very long. Again, it's been a weird day, so who knows? Maybe it'll just keep on going, and I'll have to just sit here and stare uncomfortably at you. But we're going to talk about common table expressions because I always see people misuse these, and I always get a question along the lines of, should I use a common table expression or a temp table? And the answer is always the same. It's no, because they are different things, and there's no or there. It is not an or situation. So let's look at first why we have common table expressions, and then we'll look a little bit about how they can backfire and why you should maybe just do what I do and just kind of call them dumb. So we have common table expressions. Well, not just because of this. We have them because, they were in the ANSI standard, and then Oracle had them, and then SQL Server has like the SQL Server team has a bunch of money in its budget to like have parity with Oracle for a lot of stuff, so that migrations from Oracle to SQL Server go more smoothly. So that's kind of why we have CTEs. But another reason why we have them is because derived tables have some limitations, and you can't tell by the little red squiggly lines there. This query isn't going to run. So this query will run. So I can select that ID there, and I can select this. But as soon as I ask SQL Server to join X to itself, like to say, hey, I would like to do a self join here, SQL Server says no. That is invalid. I have no idea who X is. I can't do that. We don't have that limitation with common table expressions. With common table expressions, we have that thing for the life of the select. So it just lives there, and we can join it to itself. And speaking of joining it to itself, this is where the problems with common table expressions kind of arise. I'm going to run this query where you can see I am selecting from the common table expression and then joining it to itself twice. And when I run this query, And when we look at the query plan, we're going to see that this query executed once for every join we did here. So now we have 3 seeks into the clustered index of the users table instead of 1. So the first mark against common table expressions, and this is something that I have to fight with people about constantly, which is why I wrote this demo, is that common table expressions don't materialize in any way. Like that query, anytime you re-reference that query via a join or something, you have to rerun the entire syntax inside the common table expression, which surprises people. Because when I say, okay, well, so let's look at the query plan inside the common table expression. I'm not going to run this query because it's a monster. But if we just look and we see this query plan where, you can see that we're doing like 1, 2, 3, 4 joins. We have 1, 2, 3, 4, 5 tables. And if we start like reusing that common table expression syntax, joining it to itself, we get a much, much bigger execution plan. Like this is sort of like one of those head scratches like, gee, I wonder what happened. Well, we reference every single table 3 times now. There will be badges, votes. Wait, I skipped one. I'm sorry. There's badges, votes, post, comments. We touch every single table 3 times to do those joins because we have that table referenced 3 times here. This won't stop at 3 either. This will keep going. The more joins you throw in, if I threw in 4, 5, 6, we would have 6 references to every single table in there. It would not be a good time. But that's not to say that common table expressions can never be helpful. They can sometimes be helpful, and for limited values of helpful. So let's say that we have these 2 indexes. On the post table, we have a very thoughtful index on owner user ID and ID, and we have a where clause even down to where post type ID equals 1, because if I had it do all of the post table, we might have been sitting there a little longer and it probably wouldn't have been as enjoyable for you. And we also have an index on the users table. On the users table, there's only 3 columns, but keep in mind we're selecting everything from users. But man, that index on users fits our join and it fits our where clause really well. Like if I wanted to create an index for like just this part of the query, that would be the index I wanted. I never want to create an index for this part of the query. Creating an index for this part of the query just gets you into trouble. Unfortunately, sometimes when we don't pay attention to that part of the query, we can end up with our indexes just not getting used. We can be very sad about it. Now, it would be nice if SQL Server had some like information in the execution plan or like a DMV or something like, why didn't this index get used? Like, well, what happened? Why did you ignore me? Well, it'd be nice if we had that, but we don't. We just have to guess. And here we can guess that SQL Server made, well, we don't have to guess. We can see. We can see that SQL Server made a bad guess about how many rows were going to come out of the users table. We only had 4,600 come out, but it guessed about 27,000 were going to come out. So SQL Server skipped our index because it thought it was going to have to do a whole bunch of key lookups to go get that other data. It got sick. I don't want to do this. A lot of work. I'm just going to scan the clustered index. We're just going to go there. Well, the thing is, SQL Server was wrong about that, and with so few rows coming out of the users table, it would kind of make a lot of sense to just use that narrow non-clustered index. Now, keep in mind this query ran for 1.7 seconds, right? We can see that here. Fancy new SQL Server Management Studio 18 and up on new versions of SQL Server. Woohoo! We have operator times and query plans. Anyone can tune queries now. There's no guesswork about what was slow. The only guesswork is how to fix it. It's not always just a recompile hint, I promise. It's really hard stuff to do. So let's force SQL Server to use our index. Now I'm going to tell SQL Server right here, I want you to use the users index that I created on the users table. When I run that, the first thing we're going to notice is that was a heck of a lot faster. That beat the pants off that other one. But the optimizer, being the cheapskate it is, it thought this plan was going to be a lot more expensive, so it picked the other plan. An important lesson here is that cost doesn't always add up to exactly how long a query is going to run for. I'm going to say a lot of the times it has absolutely nothing to do with how long a query is going to run for. Now, this is great. We use the index, it was a lot faster. We want to figure out how can we SQL Server to use that index more reliably. And you know what? Since since you know that we've been talking about common table expressions, you could probably guess that we're going to use a common table expression here. But I want to use the common table expression here to kind of introduce a concept that I want everyone to know about when they're writing and tuning queries. And that is to separate the columns that you're working with into two groups. You're going to have relational columns, which are columns that you're joining on, they're in your where clause, maybe stuff that you're grouping or ordering by. And then you have your informational columns. Those are columns that you're showing to users. You can totally separate the point at which you're doing your relational work from the point at which you're retrieving your informational data. And a lot of the times when you see those queries with those big, crazy long select lists, and there's just all sorts of performance problems and everything sucks, if you just broke things down a little bit, if you broke things down into, informational and relational columns, and you did all your relational work, and then later on in the query, you went and got your informational stuff, you could probably make that query a whole lot faster. So what I'm going to do, excuse me, it is a bit dry in here. It's a weird complaint since it's my office. Not even anyone else I can blame for that. What we're going to do is have a select with a very narrow list. We're not going to get a whole bunch of columns here. We're going to do our join, we're going to do our where clause filtering, and we're going to do all that inside of this common table expression. And then outside of the common table expression, we're going to join it back to the users table because we have the primary key on users, that ID column, but we're only going to join it back for the columns that we care about. And if we do that, then we can get SQL Server to use our narrow non-clustered index, right? We use that, we do a nice little seek over here. We join it to the index that we created on post here. It's a hash match, but I'm not going to get mad at that because the whole thing runs in about, I don't know, a few milliseconds. And then if we come over here and look, we have, that's still a much faster query than we had when we had it scan the whole user's clustered index, which is a bad idea. Now, the important thing to note here is we've effectively rewritten the key lookup. Under normal key lookup circumstances, I got to go back to that other query real quick. Under the normal key lookup, the key lookup has to happen immediately after we access the non-clustered index. So here we have our key lookup. Here we have our seek into the non-clustered index. This can't happen in different places when SQL Server chooses a key lookup. This key lookup has to happen immediately after we touch that index, which means we're dragging all of the rows from this key lookup around the entire execution plan, right? See that output list? That's all the columns that are coming out from the select list. And those are going to drag all through here. When we do this with the common table expression and we separate the informational work from the relational work, we can see that the key lookup happens, key lookup in quotes there because we told the optimizer to do it. There's no key lookup operator, but it's effectively the same thing because we have a nested loops join and we have the clustered index seek, which is the same thing that happened before, but now it happens way at the end of the plan. See, we have the seek into users and the join to posts, and now we've basically deferred hitting that clustered index until way at the end. We still get that whole big long output list, but we don't drag all those columns throughout the whole rest of the plan, which is kind of a nice thing. Where that falls apart, though, is if we start going back in time a little bit further. And if we go back in time further and we start having SQL Server do more work, well, we kind of lose the effectiveness of the common table expression. We can see that the plan kind of rewrote itself, right? Now we're back to we still have the seek over here, and that's good. But now we have a nested loops join to the clustered index early in the plan, so we're dragging all those columns over here again, and then we got a merge join over to the post table here, and so this is just not my favorite thing in the world because this is much slower now. That's at 3.5 seconds almost to do the same thing. And I'm not a fan of regressions because that usually means someone is going to send me an angry email when there's a regression. I don't like angry emails. I like getting paid and walking off into the sunset with a bottle of Class A Azul or something. But so common table expressions are good up to a point, but they're not stable. They're not totally stable. If we want stability, we need to use a temp table. We need to materialize a result set. We need to make the amount of work we're doing in a single step reliable. So let's check out just how quickly SQL Server can create a temp table. And I'm amazed by that every single time. Even more amazing is how quickly we can put those rows into a temp table. I am fantastic with this. I love this. 131 milliseconds. Now let's look at how quickly we can select data out of that temp table. And that is wonderful too. And the best part is that this is stable if we go back to where we remember this plan sucked before. If that took like, what, 3.5 seconds before? If we do this, it'll all happen much more quickly. We have a very quick insert into the temp table, and then we have a very fast select from the temp table. So if you want stability, and if you don't want to deal with little things like, those CTE joins causing your entire CTE syntax to be run over and over again, persist it in the temp table, you'll probably be better off. Are there any questions on that? Am I still talking to anyone? Still people there?
Most of them are still awake.
Wow, that's good for me.
Yeah, there was a question about like a little bit more zooming.
Oh, a little bit more zooming. I'm sorry about that.
I think specifically on the code. Like if you could,
Gotcha.
yeah.
No problem at all. I'm just so not used to this not being a nice big screen. Let me actually do something. This is probably going to be smarter. Let me bump this up. So the next thing I look at is this better?
That is much better. Yes.
There we go. Okay, so no more zooming. I just had to bump up the font in SSMS a little bit. All right, cool. So what I want to talk about is memory operators, and specifically how SQL Server gauges how much memory it's going to need when it asks for a query memory grant. Now, query memory grants happen for a couple very specific reasons. If you need to sort data, then SQL Server needs space and memory to write down all the data in the order you want it. And that's not just like the column you're ordering by, that's all the data you're selecting too. That's another big reason why separating stuff from between informational and relational columns is a very good idea. And so another thing that you're going to need memory for is when you need to hash data. Now, it doesn't mean if it's for like a hash, it doesn't matter if it's for like a hash join or a hash aggregate. And for both of those, you're going to need a memory grant. So what I want to start off with is showing you how SQL Server thinks about memory grants and how we can sometimes reuse memory within a query. So we've got this query here, and I should turn on query plans like a true professional. I should probably use the right database too, because it's probably a good idea, a good way to not get any error messages, right? That's like context is everything with this stuff. So I'm going to run this, and we're going to look at the query plan when it shows up eventually, and we will have a sort operator. Right, we can see our sort, and it doesn't really matter that it's spilled, but we can see that we have a sort, and we can see that that sort asked for memory. Oops, come back. There we go. Oh boy. There we go. So this sort asked for 166.5 megs of memory. Not a lot, because we only had to sort. We only had to sort to get 1,000 rows, and we're only selecting the ID column, which is an integer. So it's a pretty narrow column. We didn't have to do a ton of work here. I'm going to change this query a little bit, and you're going to understand now why I wrote it in sort of the goofy way I did, because I wanted to have two sorts in the query plan. All right, so we're going to have one up here and one down here. And when I run this and we look at how much memory SQL Server asks for, you might think, oh, well, we're doing two sorts, so it's going to be double. But that's not quite true. We do have two sorts. We have one here and we have one here, but our memory grant is only just a tiny little bit higher. And Zoom it is now going to fight with me for the rest of the night. I can feel it. So we only asked for about 160. Oh, let's call it 168. I'm willing to round up there. So we only asked for about a couple hundred megs more, or not even 100 megs, like 150 megs more there of memory. And we were able to only ask for a little bit more memory because the way this execution plan is set up, SQL Server is able to share memory between this sort and this sort. The reason for that is because this hash join up here is what we call a blocking operator, meaning all the rows from this sort all the rows from this scan had to show up at this sort. We had to sort them, and then we had to pass them over here. And when all those rows got to that hash join, we had to build a hash table on that input. While we were building that hash table, we couldn't do anything down here. So when SQL Server was done with this sort and we started building this hash table, we could pass that memory along to this sort. So this sort was actually reusing memory from that top one, which is pretty cool. And you can validate that. Right? This is where, let's do some math here. We can validate that by forcing a loop join. Loop joins do not have that same blocking property that hash joins do. So when we run this query, let's finish, which I probably should have done 10 minutes ago. That's kidding. It doesn't run for that. I think. At least last time it didn't. When we run this query, we no longer have that blocking operator anywhere. And when we look at the memory grant, now it has just about doubled to 333 meg. So that jumped way up because we couldn't share memory anymore. This sort and the two sorts needed to have separate memory. Just like a lot of smart married couples need to have separate bedrooms because no one wants to listen to that kind of snoring for 30 years and drive you insane. So we know that SQL Server needs memory for stuff. We know that memory can be shared. Now let's look at how selecting a whole bunch of columns can affect how much memory a query needs. So in case you can't read that green text, which hopefully you can because it's gigantic, you can see that as we select more columns, these are all string columns, by the way, which you should also see over there. String columns really are kind of the devil in a database. When you select data and you have to order that data in any way, you're not just, again, like I said earlier, you're not just ordering by what you say order by. You have to order all this data by this data. So when you, like, I know that internally SQL Server is not an Excel file, but you can think of a sort in the same way that you think of an Excel file. When you hit that little button in the top left-hand corner and it highlights the whole sheet, and then you hit sort and you pick one of the columns and the entire spreadsheet flips around, that's basically what SQL Server has to do here. So the more columns you select here, the more space SQL Server needs to write those columns down in. And when we get up to really big string column sizes, like here we're selecting like this column, which is an integer, which we're not that worried about, but we're selecting a display name. And if we only selected display name, we would get a 300 meg memory grant. If we selected both of these columns, we would get 900 megs. When we add in location 2, we're officially asking for 1.2 gigs of memory. And when we select all these columns with that order by, we are asking for a whole bunch of memory. That is 9.44 some odd gigs of memory just to write those big columns down. The reason for that is that SQL Server, the optimizer, guesses that every string column will be half full, and that includes these max columns. So it does that because it has to give itself a little fudge room, right? So if some of the columns are way less than half full and some of the columns are way more than half full, meeting in the middle on that is a pretty decent way to figure out how big of a memory grant to ask for. Again, really, really important, especially if you're dealing with a lot of big string columns, to separate the informational stuff from the relational stuff. Because if you have to sort all sorts of big, crazy string columns, you're going to be in trouble. Now, one thing that I want to point out that's very important, because it's something that a lot of people confuse, is that memory grants are not like the serial memory grant times DOP. It's really interesting the way that parallel plans work. So we'll run this, and we'll see that in the execution plan, we finally have a big old parallel plan, right? Look at all that nice parallelism in there. We're going parallel. We're doing bitmaps. We're going crazy. We're having a lot of fun in this parallel, a lot of parallel fun in this parallel plan. But the memory grant stays reasonably low. And right now, we're only asking for about 180 megs of memory. And that's because we do need some extra memory to sort of implement these exchange operations. So like SQL Server needs extra memory in a parallel plan to deal with the little exchange buffers and all the other stuff that goes on. So there's decent reasons to ask for a little bit more memory in a parallel plan, but we're not asking for the serial memory grant times DOP. The way that a parallel plan works is that it'll take the serial plan's memory grant and divide it equally amongst all the threads in the plan. So every thread will get an equal portion of that data, which can work out really well a lot of the times because every thread, will usually get like a a ballpark pretty close amount of work to do. But that can get really, really bad if parallelism skews and towards one thread, and you have one thread that just like gets like lots of rows and other threads that get almost no rows. Well, memory doesn't rebalance then, and that's one reason why skew and parallel plans can be such a weird performance hit, because you have no idea when it's going to happen or where it's going to happen until after you've already run it, and you're like, why did everything go terribly? And you're like, oh yeah, that one thread got 40 million rows on it. That's what it was. Are there any questions on that?
I have a lot of people looking at me like, no.
No? Okay, cool. How are we doing on time?
You have as much time as you need, no more than like 7 hours.
Okay, I can definitely go no more than 7 hours. All right, so let's talk a little bit about how we can make better use of memory, because we just talked about memory grants, and we now know that our server's memory is almost fully committed to sorting all those in varchar max columns that some god-awful developer put in all our tables 10 years ago, having no idea what they were doing, and now we're stuck with them and no one will let us change anything. The tables are all 5 billion rows now, and like we can't get the downtime to make those changes, so we're all just sad and depressed, and it's no fun. So I've written a couple views, and those views do two things that are absolutely pivotal to this demo working. One of them tells me how much data I have in an index, right? So right now I'm looking up the users table. I can see all the rows that I have. I can see how much data it takes up. It's all fun, right? Great, awesome. I also have a view that tells me what's sitting in the buffer pool. This takes a second to run. For some reason, 64 gigs of memory. Right now, probably because I just ran that stupid query up there. In the buffer pool, I have a little bit of pages from the users table, not a whole lot. We're not going crazy here. But what I want to show you is exactly how this demo works. So the first thing we do is look at the indexes that we have on the users table. The second thing we do is clear the crap out of this server, right? 5 times we drop clean buffers, checkpoint, free the proc cache. We clear this thing out. This server gets an enema. Then we look at what's in memory, and we want this to be clean every single time. Then we run a query. Oh, actually, I have to change this real quick. Ooh, I did not reset this after the last time I did this. Terribly unprofessional of me. Then we're going to run this count query, where we're going to select a count from the users table, and then we're going to look at what's in memory afterwards. So every time I do this, we're going to see what our indexes look like. We're going to get a view of how big the index is. We're going to give the server a big old enema. We're going to run the count query. We're going to, we see that's the number of records that came back from that. We have the execution plan where we can see that we scanned the clustered index of the users table. All right, good stuff there. And now when we're done, we're going to look at what ended up in the buffer pool. And when we look, we can see that we read nearly the entire clustered index of the users table into the buffer pool just to do a count, right? So obviously, you nice people out there, you're probably going to have much bigger tables and much less memory. Now, I'm lucky. I got a laptop with 64 gigs of memory of it. 300 megs is nothing to me there. But if I had, less memory, or if I had to worry about juggling more tables currently, or if my tables were much bigger, I would probably start to be a little bit stingier about what I let go into memory. Now, here's something kind of interesting. Is when let's quote this one out. And I said quote out, and let's tag this one in. Let's do a little tag team work here. So we're going to run this query now, where we're going to filter on reputation being greater than or equal to 100,000. So let's run this query, and let's see. Like maybe SQL Server will be smart and be like, look, not a lot of those rows are over 100,000. Maybe we shouldn't go and read the entire clustered index into memory, but we would be hopeless fools, because at the end of the day, that's what we do. Now, one way to get SQL Server to make better use of the memory you have is with better indexes. And that goes for all sorts of things. So what I'm going to do is create an index just on the reputation column. I make sure that got in there. I don't care that there was an error. I'm comfortable in front of you now. Next time I present here, I'm just going to wear my swimming shorts. So what I'm going to do now is run that same select count query now that we've created a narrow non-clustered index on just the reputation column. And you can see that that non-clustered index is there, it is present, it is hanging out, and it is a lot smaller. It has the same number of rows as the clustered index, but it's a lot smaller. It's a lot more densely packed. You can fit a lot more of just that single column of reputation on those 8K data pages than we can all the other crap and nonsense that's hanging out in that users table. I don't know if you remember from the last demo, we were looking at the memory grants. It's got like locations and websites and about me's. It's full of crap, just full of nonsense that I would never ever wish on anyone. But when this thing finishes and we look at what's in memory, you can see that SQL Server was able to just use a little bit of that narrow non-clustered index. Usually that primary key clustered index isn't in there. I'm not sure why that showed up this time. That's a little sneaky. But you can see that SQL Server did use the reputation index, and it read the whole thing in. I'm far more okay with having a 33 meg index read in than a 300 meg index get read into the buffer pool, though. So let's go take this one step further. Let's look at what SQL Server does when we have a filter that matches the index on the table, because this is where I think things start to shine a little bit. Now we have, again, we still have our nice narrow non-clustered index here on the much smaller number of pages, and thank God this actually worked this time. Or now we have a seek into our narrow non-clustered index, and because we were able to seek into that narrow non-clustered index, we were able to read just a fraction of the necessary pages up into memory from that non-clustered index. So we're making much smarter use of our buffer pool space by having the right indexes to match our queries. Now, this goes right back to what I was talking about earlier. We're separating the informational from the relational. We create these narrow non-clustered indexes. We let them do a lot of the filtering work. And then the data that we'll have to read in later to do other stuff can be a lot smaller. We can just read smaller chunks of things in. And that usually makes everyone a lot happier because we're making better use of all that expensive SQL Server hardware that we boss below our entire bonus on, which is not so nice. I mean, my boss would never do that. My boss would spend all my money on booze. He would never spend money on SQL Server licensing. But that's just the way it goes. Were there any questions on that? Is that someone unplugging the microphone?
That was
No.
me. That was me going the wrong direction. So
Nice.
the question that I have
Yes.
is the reason that we saw that difference is because the second plan was fully optimized and not a trivial plan, right?
No, it had nothing to do with trivial versus
Really?
full optimization. It was all because the first plan didn't have a where clause. So the first query where we just did the select count from users, it was it would have to read the entire index to figure out how many rows we had in the entire index. The second one had a where clause where it was greater than or equal to 100,000. So we could start scanning the index at the 100,000 point and only read that stuff up into data.
Gotcha. Yes, that was a great question by somebody who is not me in the audience. No, I just misread the query. So we do have a question here. What is the downside of indexing every field?
You will have a lot of problems with locking and blocking later. Usually, you don't. Usually, I would avoid a lot of indexes on just a column. I would want to have indexes that are a little bit more, well suited to the workload that we have. And again, going back, going back a couple of demos to the common table expression one, the indexes that I created weren't on a single column. The indexes that I created were ones that kind of matched the where clause and the join conditions of the queries that I'm running. I would never want to index every single column in a table on its own. That would just give the optimizer way too many weird choices. Whenever I'm designing an index, I want to make sure that I'm prioritizing stuff that's going to help me find data. So I want to prioritize columns that are in my where clause. And then I want to prioritize columns where, if I need to join that table to another table, then I'll want to have, columns that I'm joining also in in my index. And then, if there's like a short list of columns that I'm selecting, sure, maybe I can have those as includes. But most of the time, I really want to focus my indexes on the columns that are going to help me find data and relate tables together the best. Otherwise, you're going to end up with just a whole mess of locking and blocking. And the whole thing that I showed you there, where non-clustered indexes can help you save buffer pool space, whenever you need to modify or whenever you need to work with data in SQL Server, it doesn't matter if it's a read or a write, you could have a million unused indexes on a table. Well, I mean, not literally a million. You could have, I think, like 1,024 unused indexes on a table. But the second you need to insert data into that table or you need to update data in that table, even if indexes aren't helping queries find data, you have to keep them up to date with the data that's in the base table. So you can end up reading a whole bunch of unused indexes or just not very helpful indexes up into memory to keep them all synchronized with the data that's inside them. So adding a whole bunch of just sort of unrelated, unhelpful indexes can be really, really counterproductive. The other thing that you'll run into is that when you modify data in the tables, you're going to have to lock all of those indexes. Or you're going to have to lock whatever indexes are going to get modified. For an insert, that's everything. For a delete, that's everything. For an update, that's probably a more limited number. But over indexing definitely has implications for buffer pool being polluted with just crappy indexes, locking and blocking, probably deadlocks when things get bad enough. And don't forget, those are all things that you have to back up, you have to restore. You're probably rebuilding the crap out of everything in your database. You have to run dbcc checkdb on them, hopefully. There's a lot of stuff that there's a lot of good reasons not to over-index a database like that. If you really think that you need indexes on every single column, you might want to look at column store indexes because that's pretty much what you get from that.
And last question, can you share the scripts and the views to create the what we saw?
Yes, I will have those uploaded, and I will send a Bitly link to you, Kevin, afterwards, and you can share with.
Wonderful, thank you.
Yes, my pleasure. Cool. So I do want to get you nice people home to your families. So I'll run through one more of these demos that I think is particularly interesting, and this is one that I've only seen a few times in the wild. The first time I saw this happen, I was perplexed. The second time I saw it happen, I was determined to figure out what the hell was going on. And the thing that I saw, which was a terrible thing, was I saw a read query that was blocking a write query. I know what you're thinking. Everyone in the world will tell you. You run a select, it takes some locks, and it lets go as soon as it's done. It just kind of like trickles on down the table, just taking little locks and releasing them. And the query actually, it had no lock on it too. So I mean, you would think that you would be doubly sure. I mean, no lock is the wrong name for that. It should be like no respect for locks would be more accurate. But there was a no lock hint on there, so someone was like determined to not have this query block anything. Let me tell you why that happens. But first, I have to show you. First, I have to show you it happening. Show it happening to you. Pick whichever one you want. Either one's fine with me. So what I'm going to do is I'm going to have a little parameter sniffing happen. What I want to do is I want to run this query so that it gets a plan that has a key lookup in it. And then I want to run this query so that it gets a key, so that it reuses this plan, but it has to do a whole lot more key lookups. So I'm going to run this, and we're going to look at the execution plan, and we're going to see that we took 0 rows out of an estimated 3,800, and we did nothing and nothing. So that was nice. We got nothing back. That's wonderful. That's perfect. I'm very happy for everyone. Now, when we run this, it's going to take considerably longer. And the reason it's going to take considerably longer is because we are reusing that plan to get a whole lot more data, and all of a sudden, that key lookup is pretty inappropriate. So let's grab this. Let's open up a new tab, and because I'm gonna get these a little bit more organized so that I can look at stuff. But I'm going to run this query. So this is SP who is active. This is one of the most marvelous store procedures that has ever been written. I miss Adam Mechanic terribly. He's off working with Postgres now. So I don't know. Whatever, Adam. Goodbye. Don't return my phone calls. And what I have here is an update. And this will effectively update the entire votes, or attempt to update the entire votes table. Let's look at the execution plan from that select. You can see that these arrows got a whole lot thicker. We did a whole lot more work, and that whole query took round about 12 seconds to finish. So what I'm going to do is run this. I have to do this rather quickly, because if I don't, it won't look that great. I have to run this, and I have to run this. There we go. Now I'm going to kill this because I don't want to deal with that. And we're going to look here, and what we can see is this read query, right? This select query is blocking this update query. This update query is waiting on a lock. Right? We can look over at SB who is active. The blocking session ID is 71. The session ID of the select query is 71. So why in God's green earth do we have this read query blocking this write query? If you look at the locks, one of the parameters that I love for SB who is active is get_locks. You use get_locks. You know what you get? Information about locks. It's fantastic, and it's in a clickable XML column. It is like the most convenient thing, and we can see what SQL Server is doing, right? We can see that we have a shared lock that has been granted and requested on the votes table, right? So votes table has a shared lock taken on it. Shared locks like that are not compatible with intent exclusive locks like this. Shared locks like that will block intent exclusive locks. Now, normally, a read query will take a shared lock and it will let go as soon as it's done, right? Read some data, let go, let go, let go, let go, let go. Usually you don't see this kind of collision, except where there's a key lookup involved. So let's go back over here, and because we had this running, we can go back to the execution plan. And this usually makes it a little bit easier to visualize. But since we have an index seek over here, these reads will let go of locks immediately. These reads will hold on to locks until the entire query finishes. Because if we didn't, this data could get updated while we were doing this, right? While we were doing this join, this data could change. So we have to protect this data from changing while we do the key lookup. This only lasts about 3 seconds. This lasts about 5 seconds. But during this time, right, actually for the entire duration of the query, we're going to hold shared locks down here so that we can't modify data in here, right? So we have to go pull data from here. We have to bring it across here, and then, oh, come on, tooltips. Sometimes I just wish you'd go away. We have to go get data from here. We have to go get data from here. We have to bring it out over here. And the whole time that's happening, that anything that's anything that's part of the lookup is going to be blocked. Is going to block other. Has the ability to block other queries. So we can see from SB who is active, right? The marvelous, the wonderful. That while that key lookup was running, I mean, I killed this pretty. I ran this and killed it pretty quickly. But we had spent 2 seconds waiting on the lock here. If I waited a little bit, if I ran that for longer and hit F5, we would see that time tick up until about 12 seconds. And only after 12 seconds would this update be able to kick in. So if you're ever out there in the world and you see a read query blocking a write query, I want you to look at the execution plan for that read query, because I will absolutely 100% guarantee you that there's a lookup in there, and that's what's messing you up. Pretty crazy, right? Yes, no, maybe, kind of, sort of.
Yes.
Great. Thank you for agreeing with me. Anyway, it's been about an hour. I assume everyone wants to go home, drink, maybe, I don't know, smuggle some pizza out of there for their family. I don't know, whatever you want to do. I appreciate you having me. I'll get the scripts and links. I'll get the link to the scripts over to Kevin this evening. And I don't know. Thank you for having me. I hope to do this again sometime in the near future. And I don't know, if you want to get in touch with me about anything SQL Server performance related, once again, that's my contact info. I'm happy to talk about SQL Server stuff as long as I know the answer. If I don't know the answer, I'll get grumpy and walk away. I'm kidding. I'm perfectly comfortable saying I don't know. Like a seasoned professional saying I don't know. Anyway, thanks.
Thank you.
Thank you. All right, I'm going to exit.
Proof
thank you.
that
You're a
people
beautiful
exist.
crowd. Well, you could have just had that on a soundtrack. That could be an MP3. I don't want it.
Admittedly, that's true.
Yeah.
All right.
Sad. It's
So,
a sad, fraudulent world we live in.
it's all deep fakes. Eric's not even here tonight. I just did his
Nope.
voice. So thank you, everybody, for tuning in. I'm going to cut out the stream now. Our next meeting will be next week, our data science meeting, where we're going to talk about some very interesting topics. So check out meetup.com/TriPASS and tune in for that.